Let me briefly introduce you Daniele Astolfi. He received the bachelor and the master degree in automation engineering from the University of Bologna in 2009 and 2012, respectively. He, he developed a PhD jointly with the University of Bologna and Mainz Paris Tech in 2016. Currently, he is a research assistant at the University of Lorraine. And sorry. Now he was now. I apologize. In 2018, since 2018, he is a CNRS researcher at Lyon, and his research interests include observer design, feedback stabilization, and output regulation for nonlinear systems, network control systems, hybrid systems, and multi-agent systems. Okay, so thank you much for coming here, and you can go on when you wish.
So thank you a lot, Ramon, for the presentation. If you hear me, I will not use the phone.
You need to use it for...
Okay. Perfect. So I will use the phone. Okay. So today I'm going to talk about the use of dynamic saturation and dead zones in observer design and some synchronization problem. So this work I've been doing in collaboration with Luca Zaccarian, Angelo Alessandri, and Giacomo Casadei. So this is the outline of the presentation. We first introduce what is an observer problem. Then I will set up the framework, talk about saturation redesign and dead zone redesign, and finally have a short overview on some synchronization problems in which we reuse the same techniques, and finally the conclusion. So first of all, let's recall what is an observation problem. So suppose that we have a dynamical system, which is represented by this linear differential equation. So x u is some external input that we know, and we suppose that we measure an output y, and the observer problem is to try to estimate the state x by just using y along solution. So the observer, an observer is a dynamical system. Basically, what we usually do is to make a copy of the dynamics, and then to use what we call an output injection term. So this gain L that multiply the difference between the output y and the estimated y, that is used to correct the state of the observer along trajectory and to force x hat, which is the estimation, to asymptotically go to the true value of the system x. And usually in this setting, we are also interested in what is the effect of some unknown measurement noise, V, that affect the output y. So usually, the desired property that we would like to guarantee for this observer to work is that it is an ISS observer. So ISS means input to state stable, and this is the kind of property that we would like to have. So the norm of the difference between the current value of the system X, the state X, and its estimate is upper bounded by two terms. So the first is a function beta. It's a class KL function beta. Class KL means that it is increasing in the first value and decreasing in the second value. So this part is something that it's very large for t equal to 0, for instance, at initial time, because it depends on the norm on the initial error, estimation error that we have, that our guess can be bad, so this term can be large. But asymptotically, this term is decreasing because this function is decreasing in time. And then we have a second term, which is what we call the asymptotic gain, basically. So gamma is a class K function, so it's an increasing function. And this is a function just of the measurement noise. So this means that if there is no measurement noise, this observer is asymptotically convergent because this term is vanishing asymptotically. So we recover exactly the true value of x. And if there is some measurement noise, asymptotically, we forget the fact that we have an initial condition which is bad, And asymptotically, what we recover is just some boundedness properties depending on the measurement noise. So, of course, so as I was saying, beta, the function beta characterizes the performances in nominal condition, and gamma characterizes the robustness with respect to measurement noise. And of course, what we would like to achieve for an ISS observer, and would be the dream, is that beta is very fast. For instance, we may ask to have exponential convergence, and we would like the B to be very large, so that we really converge very fast. And of course, we would like to have a small asymptotic gain. So if gamma, for instance, is taken linear, we would like this gamma bar to be very small number. But in general, of course, there is a trade-off between speed of convergence and this robustness property with the measurement noise. So we cannot gain in every aspect. For instance, if we just pick linear dynamics and a Leuenberger observer, so it's just a copy plus the output injection term, we could imagine to design this gain L following different approaches. For instance, we could try to minimize the effect of the measurement noise all over the frequencies by using some H infinity design. If we know that this measurement noise has some spectral components, we could try to minimize its effect at those frequencies, and we don't care about the other. We could use Kalman filter for optimal design and so forth. But what about nonlinear observer design? So for nonlinear observer, nonlinear system, and therefore nonlinear observer, things are much more involved. So first of all, we have to recall that for nonlinear system, there are many, many different techniques. And those techniques depends basically on the property of this dynamics that we have, on the Planck's dynamics, and its uniform observability properties. So I just recall some of the available techniques. So for instance, if the system is detectable, then we can use Casantis-Cravaris Leuenberger observer. If the system is uniformly observable, we can use a high-gain observer, and so forth. But one of the main problems in nonlinear system is actually that there are few tools to analyze the effect of the measurement noise in nonlinear system. And this is due that the main reason is that in nonlinear system, we cannot use Laplace transform and Fourier transform, and therefore frequency analysis. So basically, I know very few tools that are able to analyze the effect of the measurement noise. One, of course, is to use standard ISS analysis based on Lyapunov analysis. Some time ago, we developed a technique to characterize the effect of high-frequency measurement noise in high-gain observers. But again, it was really related for this class of system. But in general, there are no systematic techniques to improve and analyze sensitivity to measurement noise for nonlinear system. And what we have in general is developed ad hoc for specific class of systems and observers. So what we want to do in this presentation, in this work, is to follow a redesign approach, meaning that, okay, give me a plant, give me an observer that you have already designed by the technique you prefer. And then I want to modify this observer to improve its performances and to improve its sensitivity to measurement noise in some sense. So we want to apply it to as many techniques as possible. And we will focus in particular on two classes of measurement noise perturbation. So the first one is what we call in literature outliers. So it's just impulsive disturbances that happen from time to time. So sporadic impulsive noise. And the other is some persistent bounded noise that may be, for instance, some white noise. And for these two kinds of perturbation, we will develop two approaches. One, which is based on the use of dynamic saturation redesign, that we also denoted as stubborn redesign in some papers. And the other is based on the use of dynamic dead zone redesign. And we will give some sufficient condition to apply this kind of a general paradigm in observer design and also actually to some synchronization problem. So this is the framework that we are going to consider. We consider a plane dynamics. W is some extra perturbation that may affect the dynamics that we don't know. V is the measurement noise, and we consider, for sake of simplicity, observer design which are made of a copy of the plant plus an output injection term, where L is the output injection gain, which is possibly time varying. Along the presentation, we will use this notation for the derivative, which is the Dini derivative, the upper right Dini derivative. It's just a mathematical simplification of, well, actually, extension of the concept of derivative for function that may be differentiable only from one side, not to the other. Just consider as a derivative. It's not very complicated. So this is the first assumption that we are going to do. So we suppose that the observer is an ISS observer characterized by an ISS Lyapunov function. And so in particular, the following three condition holds. So the first condition is that the gain L is always upper bounded. So along all the trajectory, it does not explode. Of course, this in practice is what we desire, because otherwise, if it explodes, then the measurement noise would just make everything blows up. So it's not so interesting to have increasing gain in observer design. The second condition, it's just the fact that this Lyapunov function is upper and lower bounded by the norm of the estimation error, which is what we typically use to prove convergence of the observer. So it's what I call also sandwich bound. And the third condition is the ISS condition of the Lyapunov function. So this Lyapunov function V is decreasing, is decreasing, and it is ISS with respect to the measurement noise and to perturbation. And the second assumption that we need for this framework is the following, which is what we call output growth condition. So the first condition is simply the difference between y and y hat is bounded by the Lyapunov function. And the second condition, it considers the derivative of the difference between y and y hat. And again, it has to be bounded by the Lyapunov function and also by measurement noise and perturbation error. So now this can be, it can be seem strange, but it's quite easy to show that this is in general verified for nonlinear system. And for instance, you can show it by using, so for instance, if the output is linear, well, you can just pick a Lyapunov function, which is the square root of your standard quadratic Lyapunov function. And this is why we also use the Dini derivative, because the square root is not differentiable at the origin. And so in general, these two conditions are always verified for linear system and also for nonlinear system in many cases. Indeed, the first of the two conditions simply means that we can upper bound the difference of two output from a norm of the estimation error. Okay, so this said, some remarks. In the paper that we wrote, actually, we generalized those conditions for observer dynamics as have possibly a larger dimension of the plant. This is because in many observer techniques, we also do immersion and so on. And it covers a long list of observer design techniques that exist for nonlinear system. So it is quite general. So let's go to the first result of this presentation. So first of all, in this image, we can see the outliers. So we suppose that we measure, this is the output y, and from time to time, the output y is affected by an outlier. So some sporadic measurement noise that we would like to ignore somehow. So we consider the observer, and we denote EY as the difference between the y and the y hat. Now, the main idea is the following. Suppose that EY is very small for a long time, for a long time. Well, then this means that the state of the plan and our estimate are close. So actually, we don't want to use the correction term. And now suppose that EY is large, but for a very short amount of time. Well, this could be due to the effect of measurement noise of an outlier, and not because we are bad estimating, not because the observer is far, the state of the observer is far from from the state of the plant. So again, we don't want to use the correction term. But now, if this EY is large for a long time, well, this means that actually the observer then state is very far from this plant state. So we do use we do want to correct, to use this correction term to make the observer convergent. So based on this idea, the main principle is to use this block between the y minus y hat and the observer. So now if we analyze this block, we see that instead of feeding the observer with EY, we feed it with EY bar. So this EY bar is the saturated version of EY. But now the important thing is that this saturation is adapted to the threshold of the saturation is sigma. And actually this value sigma is adapted online, by a dynamical equation. So it's not a fixed saturation, but it's a saturation whose value evolves along time. Now the dynamics of the saturation, so sigma, is stable and it is fed directly by this error EY. So the principle is that, so what happens now if we have an outlier? So if EY is persistently small, the level of the saturation becomes small. And so the saturated version of EY is small itself. It means that we are small for a long time. So we are in the sense that we are close to the right solution. So we don't have to use the correction term. Now, if an outliers arrive at a certain times, well, EY will become very large. But actually, the level of the saturation is still very low. And so this means that actually we filter it through the saturation. And now, if now EY becomes large for a very large of time, because we are far, the observer is far from the state dynamics, well, this sigma variable will increase because it's fed by EY, which is large. So sigma becomes large, and then we desaturate. So we use the standard correction term to make the observer convergent. So this was the main idea, and we have the following theorem that simply say that if you consider a system and an observer, which is ISS with the Lyapunov ISS condition, and it has this output growth condition, then if you apply this redesign technique, so you feed the observer with the saturated version whose level is dynamically adapted, well, you will obtain an observer which is still ISS and which still satisfies this output growth condition. So you preserve the original properties of the plant. Of course, in the multi-output case, you can saturate each output component-wise and have multiple levels of saturation. So now this very nice from the intuitive point of view, but we don't easy to working. So just a few remarks. So we preserve the ISS property. The proof is based on a construction of a Lyapunov function. So the two questions: is the new observer really performing better in presence of outlier? And how to select also the parameters of the dynamical saturation. So let's make this simple noise analysis for linear system. We consider a linear system, okay, a linear plant. We consider a Leuenberger observer, linear, and we apply our idea of a redesign with the saturation and the sigma saturation level. And we put in this scenario in which we consider initial condition of the estimation error, which is 0. So we suppose that we perfectly know the initial condition. We put we put at 0, and we apply an impulsive measurement noise to see what happens and to try to compare the difference from the original observer and the redesigned one. And we also will analyze the constant noise case. So we have this result is that now if V is modeled as a delta direct impulse of length tau, which is basically this, we consider the two solutions of the two observers. So x0 tilde is the estimation error for the original observer, and x tilde sat is for the estimation error for the redesigned one. We put at 0, we put sigma at 0. We apply the impulse, and we check what happens to the solution in the tau instant of time. And what we can prove is that at time tau, the tilde x sat, so the estimation error that we do with the redesigned observer, is smaller than the estimation error that we do with the original observer multiplied by tau. So this means that if tau, remember, is a delta direct, so tau is something very small. So if tau turn to 0, actually this go to 0, and actually it means that we really improve a lot better. So we improved this show that in general for tau small, we improve the performances in presence of outliers. If the outlier is instantaneous, we filter it completely. And recall that after time tau t larger than tau, there are no more outliers. So what we have is the evolution of the two observers without measurement noise, but the redesigned one started from an initial condition, which is much smaller. Well, the estimation error is much smaller than the other. The other result that we have is that if we consider some constant perturbation, well, the DC gain of the observer with respect to this constant perturbation is the same. So it's not worsened. And this is also a good point because we know that at least in this scenario, we cannot do worse than the original system. So this is a simple simulation now to show how it works. So we consider a linear oscillator fed well, u equal to, so there is no input. We make a Leuenberger observer. We applied our technique, and now we look at the effect of the perturbation. And the perturbation, so between 0 and 20, there is no perturbation. Then at time 20, we apply a delta Dirac. And then from 40 seconds, we apply the constant noise. So what we see at the beginning is the effect of the initial condition. So in blue, there is the original observer, and green and red are the redesigned one with some different choice of parameters, just to compare what happens when we select different parameters. We see that the transient behavior at the beginning is a little worsened with respect to the blue line, and this is because of the saturation. So in general, we degrade a little the transient performances. But then when we apply an outlier at time 20, we see that the red one is nearly not affected by the outlier, while the blue one, which is the original observer, goes very far because we have a large impulse, so it goes very far, and then you need to recalibrate because of there is no perturbation. And finally, when we apply a constant perturbation, we see that we end up actually to the same value, so we are not doing worse in this case. So the takeaway message of this saturation redesign is the following: pick any observer you want, add this dynamical saturation, and you will degrade a little the transient performances of the observer, but you will really improve the performances in presence of outliers. So it remains just to how to tune these two parameters, lambda and sigma, lambda and theta, sorry. So lambda, we see, is the speed of the convergence of the sigma. So if lambda is too small, we may deteriorate a lot of the performances because it will adapt in a really slow way. So this means that what we give to the observer design, it's a filtered slow version of the correction term. So we may also lead to instability. So lambda should be selected according to the observer dynamics, basically. And theta, well, this is how we reduce actually the effect of the measurement noise, because since we saturate to the level of theta, if we look at the DC gain of sigma, it is just theta over lambda. So if lambda is very large, we would like this DC gain to be 1 or even smaller. So we would like to reduce this gain, and therefore to maximize lambda over theta. But if we reduce it too much, then it means that in nominal condition, we saturate too much, and so we are not giving enough, let's say, control power to the observer. So again, it may lead to instability. So we need to be careful in how to select the parameters. So actually, in the proof of the theorem, we prove that if you fix theta, there exists if you fix lambda, there exists theta large enough so that everything will work. So it's not so difficult to prove things from the Lyapunov theory. Now, the second idea that we came out is the use of dead zone redesign. So the use of dead zone is motivated by persistent small noise. Why this? Because now suppose that EY is, for the nominal observer, EY is small for a very large amount of time. Well, if there is some perturbation, which is small, well, this means that actually EY is just the noise. We are just using the noise to correct our observer. Because if EY is large, it corresponds to initial conditions which are bad. But if it's always small, well, this is just noise that we are using to feed the observer. So again, we would like to cut and don't use this information. It's just useless. So this can be done by use dead zone. So what is a dead zone? I recall here in the picture is just this function, which is 0 between minus a and a, and then it's just linear. And again, the idea is just to use a dead zone whose level is adapted according to a dynamical system which is fed by this output injection term. So the idea here is that the sigma will reduce the output EY. So I should have written here. So if sigma is smaller than EY, then the dead zone is not active. But if sigma is larger, then it's 0. So this is the cutting effect that we look for. And well, I will make the long story short. We just have another result, which say that if you pick an observer which is ISS and respect the output growth condition, you apply this dead zone, which is dynamics, and you still preserve the fact that you obtain another observer, which is ISS, satisfying the output growth condition. Again, we can also think about having multiple outputs, so cut at each output. So the previous theorem show how to preserve the ISS property and give sufficient condition for the choice of the two parameters that characterize the dynamics. The proof is again based on a construction of a Lyapunov function. Again, two questions arise. Is the new observer performing better in presence of persistent measurement noise? Second question, how to select these parameters in practice. So for this, I will just go short and I will just present this simulation. Again, we use the previous example in which we have the oscillator. We use a Leuenberger observer, and we apply some measurement noise, which is 0 in the first 20 seconds to see the effect of the transient behavior when we have different initial condition, then 0. Then we apply a constant perturbation from 20 to 40, and then from 40 we apply a sinusoidal signal as a measurement noise. And what we see is that again in the transient we degrade a little the performances, but then for constant perturbation we improve it, and because of this cutting effect of the dead zone we are actually modifying the DC gain from the constant perturbation to the estimation error. So this is why we improve. And then at the end, well, we don't see what's happening, but so I reported the data here. The blue one, again, is the original one. And we see indeed that by selecting the parameters, we reduce the effect on the estimation error when we apply sinusoidal perturbation. So again, the takeaway message is pick any observer that you prefer. You know that there will be some persistent noise. Apply this dead zone redesign technique. Trade-off, of course, you degrade a little the performances, but you improve the sensitivity to measurement noise. And concerning the tuning, well, again, we have that lambda is how you fast adapt the level of the dead zone. So you would like to select lambda according to the observer dynamics. And then the larger is theta, the larger is the cutting effect. So if you cut too much, again, you lead to instability because you don't give the right signal to the output, to the observer when you have to really correct because your initial conditions are far. So you have to tune a little this. So this is another possibility, of course, because since you preserve the ISS condition and the output growth condition, you can also mix the two approaches and make first dead zone and then saturation in order to improve with respect to both kind of perturbation with two different adaptation. So now what is nice is that actually it is known that observer design is also linked to synchronization problem. The two theory are very similar in some context. So we apply the same ideas of using this saturation and dead zone techniques in a simple synchronization problem. So the synchronization problem that we look at is simply the following. So we have a network of agents. These agents, the dynamics are homogeneous, meaning that they are all identical. And we want to use to synchronize the network so that all the xi converge to each other. So they converge to the same value. So we want to achieve what is also denoted as consensus. And a typical approach in doing so, at least in output feedback approaches, is to use some kind of diffusive coupling, meaning that you just correct your dynamics by using your output, the difference from your output and what you see from the agents from your neighbors. Okay, so then there is theory that tell you that everything can work. Of course, what you would like to obtain at the end of the story is something which is ISS with respect to external perturbation that may arise everywhere because of communication. There can be some noise in the communication network or in the dynamics and so on. So what you would like to achieve again is some kind of ISS property with respect to this external perturbation. And so, well, again, what we have done is to reuse the same idea. So each agent now, instead of using the linear coupling term, it modified it by adding this saturation or dead zone redesign. So you correct it by a smart way, let's say. I will not give the theory because basically the theory is the same in the sense that if you have a network and you make your design so that you achieve consensus in an ISS way, you apply the redesign technique and you preserve your ISS condition. I will just show some pictures because, yeah, as I wrote, proof and philosophy design are very similar. And so in this simulation, we consider a network of 6 linear oscillators, which are coupled each other so that to achieve consensus. We show the estimation error from the 6 estimation error that we have. And the first picture shows what happens without redesign in presence of outliers that happen each 5 seconds. And the second picture, it's the same initial condition, same noise applied to the synchronization networks, but with the saturation redesign technique. And we see that actually we reject much better and all the states remain close to each other much more with respect to the original design. This is also nice to see, which is the norm of the input. So it's the energy that we put to correct. And we see that when there is some outliers that happens, we use a lot of effort to remake the state converge to each other, while in presence of this saturation redesign, we need less effort to make it converge. And now this is another simulation in which we used the Van der Pol oscillator, so which is nonlinear, and we applied some white noise in this simulation that happens each so for 10 seconds, each 10 seconds there is white noise, and again we see the difference from nominal design and the design with the dead-on redesign technique that we applied. And again, in this case, the solution remain close to each other better than the nominal design. And also the effort that we put to control the system, it's less important due to the dead zone effect that cut the measurement noise. So I'm going to the conclusion now. So we provided a very general framework based on these two ideas of using saturation and dead zone to improve performances. what I really liked about this idea is that nonlinearities are used to improve performances, while in general we see nonlinear as bad, something that destroyed our properties. So it's the opposite, and it was really nice to be involved in this work. So now we are currently using the same approach to prove that in an output feedback context everything will work. So you have a plant, you have some measurement, you want to use make output feedback control. Can I add this saturation or dead zone in the loop to improve performances in output feedback control? Well, the answer is yes. It's not surprising, but we are still finishing to write the paper. And just to give some idea, is well, it would be nice to see what can we do with other kind of different nonlinearities to improve performances in presence of measurement noises, and how nonlinear can be good in some sense. And this work was a summary of these 3 papers that appear in the last 2-3 years. Thank you a lot for the. So if you have any question, don't hesitate. Yes. No. Yeah. Yes. Well, actually, when you apply the saturation redesign, is because you expect to do something better in presence of outliers. And when you apply the dead zone, is because you know it's persistent. So yes, we are using some kind of information of the noise. You don't assume to you don't need this kind of information to show that the redesigned observer works, of course, but you use it in order to design your filter somehow. But of course, using some kind of different information, I don't know, maybe some spectral information, or I don't know, maybe some different type of nonlinearities could do also a good job. Mm-hmm. 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 Yes. Yes. Mhm. You will recorrect again. Yeah, no, we have not studied it, but I mean, it's always a trade-off between how you trust your output signal and your model. It's a compromise, and it's a trade-off between these two, because if the signal is so if the difference between your estimation output and your output is small, you can assume you're doing well. So there is no point in correcting. And if it is increasing, the dead zone will adapt, and then you will start to reuse. What is nice is that it is not really a switching mechanism, but it's smooth because of the dynamics. So at least everything will be smooth. But I hope it was everything very clear.